So I'm going to be talking about light in low Reynolds number. Basically, it's going to be based on the paper that Ian Purcell has published in the 70s, in June 1976. And in this paper, it was one of the memorial lectures. He was trying to summarize all the ideas that we could have about flows in the low Reynolds number. But before we delve into this topic, I'll just derive what does it mean. What is low Reynolds number? What is Reynolds number at all? And where does it come into picture? So I need to define some things to make it understandable, because otherwise it will be just hand waving. So I need to derive the advective derivative, which is just the derivative of a parcel following the fluid. It's used in fluid mechanics quite a lot, and I'm going to do all the maths in the next 5 minutes, and after that there will be just pretty pictures and videos. So this is the advective derivative. And it defines how does the motion change as you follow the parcel of the fluid. Does it accelerate or does it decelerate? If the parcel of the fluid moves with constant velocity, the advective derivative is going to be naught, because then the velocity doesn't change. And then, if you want to just use the Newton's second law to define what happens when you have a parcel of fluid which moves in certain direction, just a parcel enclosing some particles of the fluid, then you can think of Newton's second law, so force equals mass times acceleration. If anything is not clear, just shout. And the mass can be written as density times change in velocity, change in volume, dV. Acceleration can be written as the advective derivative, du dt. And this must equal the force, which is driven by the pressure gradient, and buoyancy, which is defined by gravity.
Sorry, Chris.
Yeah?
Did you say that it defines the change in velocity of a single particle within the fluid?
We consider just a parcel of fluid, which has got the volume delta V.
Okay.
That's why I write everything in terms of delta V, because I think what happens to a small parcel of fluid which has got the volume of delta V.
Okay, and the idea being the volume is so small you can treat it as being not something that's going to...
Yeah, then I'm going to take the limit to naught, and
okay. Sweet.
It's going to work out as a normal integral. So this already enables me to write down one of the first equations of fluid. It has been written in 1700s by Euler, and it's one of the first ones. It's just rearranging the terms here, which gives you the du dt. The rate of change of velocity of the parcel as you go along the parcel is minus the gradient of p plus kappa, when I define kappa to be the potential for the gravity, because it's nice to be able to put here scalars here inside, and that's why I want to pick out the del. And this is the Euler-Lagrange equation. Sorry, just Euler. Euler-Lagrange comes into play in a different branch of physics. Now, this defines only the motion of parcel without any viscosity. So it is an inviscid fluid. It doesn't really appear in many applications in physics, especially in low Reynolds number, when we're going to have highly viscous fluids. So I need to add the viscosity to it, and the way it goes. Where is the eraser? Yeah, this works. I'm going to copy that equation. The way I do it is to think, how do we actually express viscosity? So the shear stress is the coefficient of viscosity times the change in velocity. It is just when you think of a fluid having different velocity profile as your height changes. This would be u of y. The differences in velocity in the fluid also defines the different momentum carried by the particle at different height. That's why you can write that the shear stress divided by the density is going to equal the mu over rho. So I'm just copying that from here. The grad of u, because this is just one of many components of u, you can have components of momentum in all possible directions. This was the initially simplistic assumption that we are going just in one direction, because we could go in all possible directions, and that's how d dy changes into grad, and this equals by definition to mu grad u. So we just define mu to be equal mu over rho, and mu is called coefficient of viscosity, and this is called the coefficient of kinematic viscosity, which is most often used in all the papers and in the research work. And this is called just the coefficient of viscosity, and that's the density. We can also say that the shear stress is force acting per area on the fluid, trying to rotate it, trying to do something on it. So it is actually a force per area of the fluid. And that's why we can write the difference in forces acting at different level of the particle. Rho v du dy at one height plus that. So this would be at a higher position, and this term would be at lower position, which in total gives me rho v du dy, and therefore viscous acceleration which I defined as mu force per mass from Newton's second law would equal. I try to expand it because I know that what I have is force per area, that, and I'm trying to figure out what is force per mass. So I should better be able to express the viscous acceleration in terms of tau, which is F over A. So I try to express mass in terms of area and stuff. So it's obviously area times length times density. So it's volume times density, which gives you mass. I have force per area, it is tau. And when I substitute from above, rho nu and du dy, length would be dy, and density is rho. Density cancels. I get the second derivative dy, and mu stays in its place, so I get d squared u dy squared, which proves that the viscous acceleration is just the second derivative of my velocity field. So tau in general would be del squared of u. And this is the term that I was looking for. This is the term that I need to add to the Euler equation in order to account for all the viscosity of the fluid. Are you still with me? Yeah. Happy. It's all the maths, but I could have said that this is the term that accounts for viscous acceleration or deceleration, but I wanted to show where does it actually come from. Is it clear?
So it's an acceleration of this water parcel.
No,
Due to viscosity.
Yeah, acceleration or deceleration, because if it is viscous, then it is actually dragged by the viscosity, and it's always expressible by mu times del squared of u. It is not the same tau. I should have maybe called it in some different way, maybe a v or something like that, because it has dimensions of acceleration, force per mass. Force equals acceleration times mass, so this surely has dimensions of acceleration. So going back to Euler, I need the whiteboard. We had that the rate of change of the fluid properties following the parser as you go in a velocity field equals minus grad of p over rho plus chi, and then I have to add the term of mu of viscous acceleration.
Actually, what's that term, Chris? That sort of cross?
Which one?
You saw chi.
Chi. This is the gravitational potential, because I wrote down that here you had g, rho g. Rho gh you recognize as the buoyancy, and I had here that d u dt equals minus grad of p, and it was multiplied by that, plus g rho, but then I divided by rho, so I got just g. So I have now this du dt on the left hand side equals minus grad of p over rho. Rho is a scalar, so it doesn't change the grad, plus g, and g is minus grad of chi. It could be called phi. Quite often it is called phi, the gravitational potential.
Okay.
But I just used chi because it's just a letter, and in fluid physics they usually use phi for the velocity potential instead of gravitational potential.
Okay.
That's why I used chi, but it is just gravitational potential, it's just for simplicity. And then I cancel it anyway because I say that at such motion for small animals it just doesn't matter, because they are almost in the same gravitational potential, on the same on the equipotential surface, so it doesn't really matter at all.
Okay, I guess I intuitively don't understand what this du dt is.
Well, here,
Here.
if you write any function df dt, it is just defined as df dt plus u dot del f. So effectively, if you write it down in full, it's going to be u. If I define u to be u v w, it's going to be u df dx plus v df dy plus w df dz. So this is the term.
And what is uv and w?
U, V, W are components of your velocity field. So if you have a fluid
In x, y, and z directions.
in x, y, and z directions, you have x, y, z, and you have a fluid going somewhere, and it's going to have a velocity field of u, which is a vector, which has three components, u, v, w. So this actually tells you how a quantity, so it is f. F is just a function, any quantity. You could think of anything that you could define along the fluid, changes in temperature, for instance, anything, any scalar quantity, or anything that can be defined at every single point of the fluid as you go along. So this would just tell you how does this quantity vary as with regards to the motion of the fluid. So if I'm going along the fluid, first, how does it change in x direction? How does it change in y direction, and how does it change in z direction? Because it might be that I'm just interested in the collective way, both what is the magnitude of the velocity of the fluid in that given direction, and the change of that parameter that I have defined along this distance. So if you do a temperature, you would be thinking about what is the velocity in x direction times the change of velocity in x direction, then plus the velocity in y direction times the change in this temperature in y direction.
But u is a vector.
Where?
U is a vector.
Yes, u is a vector, but I'm now thinking only about its components. So u, v, w are components of the vector. To confuse you, because it's the same u, but this one is underlined.
Yeah,